Hello, my name is chandramouli. I am about to present my seminar on the topic metal carbonyls. So, let's get started. At first, let's take a look at the contents. Now, metal carbonyls are the transition metal complexes of carbon monoxide containing metal carbon bond. Lone pair of electrons are available on both carbon and oxygen atoms of CO ligands. However, as the carbon atom donates electrons to the metal, these complexes are named carbonyls. Though CO is not considered a very strong Lewis base, yet it forms a strong bond to the metal in their complexes. CO may bond to single metal, or it can act as a bridge between two or more metals. The number of CO ligands coordinated to the metal is generally in accordance with 18 electrons rule. The 18 electron rule is followed by almost 99% of metal carbonyls. Classification of the metal carbonyls. Classification on the basis of ligands. Metal carbonyls can be classified into two categories: homoleptic and heteroleptic carbonyl complexes. Homoleptic carbonyl complexes are those in which metal is bound to only CO ligands, for example, nickel CO4, and heteroleptic carbonyl complexes are those in which metal is bound to CO as well as other ligands like molybdenum CO3, PF3, chromium CO2, NO2, etc. Classification on the basis of number of metal atoms. Mononuclear metal carbonyls. These carbonyls contain only one metallic atom, and these carbonyls do not contain any bridging ligands. Examples of these are nickel CO4 and chromium CO6. Polynuclear metal carbonyls. Polynuclear carbonyls contain two or more metal atoms. These are further classified as homonuclear metal carbonyls and heteronuclear metal carbonyls. Homonuclear metal carbonyls contains metal atom of only one element, for example Fe2CO9. Heteronuclear metal carbonyls contain metal atom of different atoms like MnCO, CO4. Now, let's take a look at the molecular orbital diagram of CO. There are 2 electrons in the 2p orbital of carbon and 4 electrons in the 2p orbital of oxygen. Now in the molecular orbital of CO, 4 electrons in the pi molecular orbital, which is of lowest energy, and 2 electrons in the sigma molecular orbital are present. So we have a vacant pi star and sigma star molecular orbital. Sigma is the homo or highest occupied molecular orbital, and pi star is the LUMO or lowest occupied molecular orbital in this case. Bonding in metal carbonyls. CO is considered to be a good sigma donor as well as a pi acceptor ligand. The metal carbon bond in metal carbonyl possesses both S and P characters. The metal carbon sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into a vacant orbital of the metal. The metal carbon pi bond is formed by the donation of pair of electrons from a filled d orbital of metal into the vacant antibonding pi star orbital of carbon monoxide. The metal to ligand bond creates a synergic effect which strengthens the bond between carbon monoxide and the metal. Consequences of bonding. When the metal in the metal carbon complexes donates its electron to pi star antibonding orbital of CO, it forms a double bond between metal and carbon. So, with this increase in bond order, metal carbon bond length decreases and bond becomes stronger. For the exact same reason, bond order of CO bond decreases and becomes more weaker. Evidence of back bonding. Infrared spectroscopy is extensively used to characterize metal carbonyls since the CO bond stretching frequency gives very strong sharp band in a very unclouded region of spectrum. The vibrational frequency of a bond depends on the strength of bond, which is measured by the force constant. In the equation, V bar is equals to 1 by 2 pi c root over k by mu. Here k is force constant, mu is reduced mass. For atoms of mass m1 and m2, reduced mass is m1 into m2 by m1 plus m2, and c is velocity of light. From the above equation, we can say V bar is proportional to root over of force constant, or k. That is, as the strength of bonds between two atoms increases, stretching frequency of the bond increases and the frequency of the corresponding bond will be higher in the IR spectrum. From the equation, it also clear that V bar equals to V bar is inversely proportional to 1 by root over reduced mass. That is, as the reduced mass of the atoms increases, stretching frequency decreases. The stretching frequency of free carbon monoxide free CO is 2143 semi-inverse. On the other hand, it is 2000 semi-inverse for chromium CO whole 6. The explanation of this is that the back bonding populates the pi star on CO and reduces the bond order of CO towards 2, and therefore resulting in lengthening and weakening the CO bond. Factors affecting stretching frequency. Various factors that affect stretching frequencies are charge on metal, number of ligands, and presence of other ligands on metal. First, let's talk about charge on metal. Higher electron density on the metal will cause an increase in the extent of back bonding. This leads to an increase in electron density in pi star orbital on CO, lengthening and weakening of CO bond and a decrease of the CO bond frequency. Higher the formal negative charge on the metal carbonyl, more will be the tendency of metal to donate electron density to pi star on CO. Therefore, stretching frequency of CO decreases and stretching frequency of metal carbon bond increases. In the same way, higher the formal positive charge on a metal carbonyl, lower will be the tendency of metal to back donate electron density to pi star on CO. Therefore, CO bond order and CO bond strength increases, hence the stretching frequency of CO bond also increases. Number of ligands. As the number of CO ligands attached to the metal increases, the formal negative charge on metal increases. Therefore, the extent of back donation increases and hence CO bond stretching frequency decreases. Presence of other ligands. If a ligand L is a strong sigma donor and weak pi acceptor, or a pi donor, or a sigma donor, or a sigma as well as pi donor, it will supply electron density on metal, and this increased electron density on the metal will encourage back donation and leads to shorter and stronger metal carbon bond and longer and weaker CO bond. Consequently, the metal carbon stretching frequency increases and carbon dioxide stretching frequency decreases. Let us consider, for example, two complexes, chromium CO whole 6 and chromium CO whole 3 and NH3 whole 3, In both complexes, chromium has a formal charge of -3 and back donation occurs. However, because NH3 has no orbital available for accepting electron density from the metal, all of the back donation in the complex chromium CO3 NH3 goes to the CO ligands. In the complex chromium CO6, the back-donated electron density is spread among 6 CO ligands. Because of this difference, the CO bond stretching frequency in chromium CO6 is obtained at 2100 semi-inverse, whereas in chromium CO3 NH3 is obtained at 1900 semi-inverse. So I took references from these books and other internet sources. So finally, I would like to thank my professor Abhishek Shaha, who gave me this opportunity to do this project on the topic metal carbonyls. Thank you.